So we've had a brief stint with quadratic expressions, equations, learned some rudiments, solved a few basic elementary problems on quadratic expressions, equations. Just to get guided into a more mature understanding of the same, we move to the present sheet titled Ollie Poly. Okay. Simple problems, not as fancy as the name suggests, but let me illustrate a little bit before I leave you independent with the sheet. Let me illustrate, let's say, the first few problems so that you gather the momentum required to move to the next problem of the sheet. Okay. Refer to problem 1, Ollie Poly. We want to find the values of P, we want to find the values of the parameter P, for which 2 log Px plus 28 to the base 1 by 25 equals minus log 12 minus 4x minus x squared to the base 5 has only one solution. That means there is only one value of x that satisfies this equation. First of all, let me tell you the meaning of one solution. One solution could also mean, in addition to having the usual single value of x satisfying this condition, it could also mean two coincident values of x would mean two roots but one solution. See, for example, if I have an equation x minus 2 whole squared equal to 0, it has two roots, 2 comma 2. It has two roots, 2 comma 2, but one solution. The solution is 1, but two roots, they're coincident roots. Two coincident roots would actually mean one solution, right? That's the first jargon that you must understand. Second, just in case you've forgotten all about logarithms, log b to the base a is log b to any base divided by log a to the same base, right? And therefore the left hand side could be rewritten as log 2 log px plus 28 divided by log 1 by 25, log of 1 by 25, that means 5 to power minus 2. That means this could have been written as, this minus 2 will come here, right? So if this minus 2 comes here, this would become minus log px plus 28 to the base 5, yes or no? Because see, this 2 will get cancelled with this 2, minus log a divided by log b now, which is log a to the base b, yes or no? Right? So the left hand side would reduce to this. So just to algebraically simplify the matter here, this is like minus log px plus 28 to the base 5 equals minus log 12 minus 4x minus x squared to the base 5, yes or no? That's an equivalent equation, right? And we want this equation to have one solution. We want this equation to have one solution. Okay. Now, so just to save some space, I'll just modify this to match what's given. This is what we have, right? Log px plus 28 to the base 5 is log 12 minus 4x minus x squared to the base 5. We want this equation to have one solution, right? Now, which means you might be tempted to believe the following. Of course, if log A is log B, then A must be B, right? Which means px plus 28 must be equal to 12 minus 4x minus x squared, right? Which means x squared plus x into p plus 4 plus 16 equal to 0, right? Yes or no? Let me call this expression x squared plus x into p plus 4 as fx. This expression, let me refer to that as fx, right? Now, what is it that we are trying to do here? This quadratic can have roots of different natures depending on p. One, it can have both real roots, it can have both complex roots, and of the two real roots that it has, it could also have both roots coincident. It could have both roots coincident, right? Now, which means, you know, this cannot have one real and one complex root. Yes or no? This equation cannot have one real and one complex root. That means it's not possible that it has only one real root. So, in general, it will have two real roots, x1 and x2. We don't want, give me a little while to explain matters. I know what we want. I'm sure by the time I progress a little bit, I would have answered your question. I know your question. Okay. But I'm moving in that direction. Trust me on that. Okay. x1 and x2 are the roots. Now, what we don't want is both roots of this to be complex. That we surely don't want. Because if both roots of this are complex, then this has no solution at all. Yes or no? So that's not something that we want. We certainly want the roots to be real. Right? No, equal or not, you'll understand. That's one possibility. That does not cover all possible situations. That's one possibility which you will understand. x1 and x2, the roots of this, for sure must be real. Because if both are complex, then this will have no solution at all. Right? So let me first reduce the processing window for p. In order that both roots are real, the discriminant of this must be greater than or equal to 0. Right? Which means p plus 4 whole square minus 64 must be greater than or equal to 0. Right? Which means p plus 4 must be greater than or equal to 8, or p plus 4 must be less than or equal to minus 8. Right? That means p greater than or equal to 4, or p less than or equal to minus 12. Yes or no? Right? So for sure, and when p is equal to 4 or p is equal to minus 12, this will become equal to 0. That means p equal to 4 or p equal to minus 12 will give me equal real roots. Yes or no? Right? Now, so for sure, let me, I'll remove this from here. I'll just mark discriminant greater than or equal to 0 gives me p greater than or equal to 4, or p less than or equal to minus 12 is what's obtained. For sure, whatever we are trying to do must subscribe to this condition, because we are not talking of both roots complex. So we must limit ourselves, restrict ourselves to only these values of p in our further assessment of the situation. Got me? Now, and for sure, when p will become equal to 4 or p will become equal to minus 12, this discriminant will become equal to 0, and p equal to 4 and p equal to minus 12 are quiescent points towards having equal real roots. Right? Okay. Now, can I remove this? Now, look. This expression, even though this equation has two real roots, right? It's possible that of the two real roots x1 and x2 that this quadratic has, one of the values will cause this expression to be negative. Yes or no? This equation, this equal to this, has two real roots, right? That means this expression will become equal to this expression for two values of x, which is causing this quadratic to become 0, right? So it would temporarily make you believe that the two roots of this x1 and x2 of this equation are also the roots of this logarithmic equation. Now that's far from true. In fact, that's not necessarily true, because maybe the two roots of this are such that will cause this expression to become equal to this expression. But let's say one of the values, x2, one of the roots, x2, causes this expression, the right hand side expression, to be negative. Now if it causes this x2 to be negative, it will still be the root of this equation. But if x2 causes this expression to be negative, then the logarithm of this expression will not be defined. And therefore, even though x1 and x2 are roots of this, only x1 will be a solution to this. Yes or no? Are you there with me? Right? So you understand the whole game now? What exactly we are trying to achieve here? I'm saying x1 and x2 are the roots of this equation. x1 and x2 will cause this expression to be equal to this expression. And that would make you believe that x1 and x2 will also satisfy log of this equal to log of that. Right? I'm saying not necessarily. x1 has caused this to be equal to this, x2 has caused this to be equal to this, but let's say at x equal to x2, this expression is becoming negative. One of the roots, let's say, is causing this expression to be negative. Now if x2 causes this expression to be negative, then I claim that this will not be a root of this logarithmic equation. Why? Because then log of a negative number will not be defined. So now if you found x1 and x2 roots of this, and you plug in x equal to x2, and you find that this is becoming negative, then it's not a root. It's not a solution to the logarithmic equation. It's a solution to the quadratic equation, equivalent quadratic equation. It's not a solution to the logarithmic equation. Right? Which means one thing that we are trying to do here is we are trying to judiciously select p. We are trying to judiciously select p such that of the two real roots x1 and x2 of this quadratic, one root x1 is legitimate and will cause this expression to be positive, but the other root, which is also a root of the equivalent quadratic, but the other root x2 causes this expression to be negative, and therefore that root x2 which appears out of the quadratic can be rejected, and this leaves us with only one solution to this quadratic. Yes or no? Yes, sir. Right. The other possibility, so this is one case, right, of the two real distinct roots, one root will cause this expression to be negative, then those are values of p that we have to track. Okay. Then the second profiling of the whole thing could be done in a manner that x1 and x2, the two roots, are equal. which happens for p equal to 4 or p equal to minus 12, right? And those two roots that are equal must lie, those would be looked upon as one solution. Two roots but one solution, and those two roots will cause this expression to be positive. Will cause this expression to be positive, right? Now, based on this premise, let's go ahead and build it up. Let's go ahead and graphically build it up. But have you understood the philosophy of the whole thing? Right? Then those are values of p that are not relevant. We want at least one root. If the two coincident roots are causing this expression to be negative or 0, then those are not of value to us. Isn't it? We want at least one real root. So then that case will be rejected. Yes, and therefore those would be rejected. Therefore those would be rejected if that happens for some p. It can happen, yes, and we will therefore come out up front and battle it out. Okay. So now let me look at, so what we are seeking is, of the two roots x1 and x2, one will cause this to be greater than 0, the other one will either cause it to be equal to 0 or less than 0. Then the one that causes this to be greater than 0 is of concern to us, is of value to us, and will produce the single solution that we are seeking to this logarithmic equation. Huh? No. See. Realize that px plus 28 and 12 minus 4x minus x squared, they are equal, therefore they will always have the same sign, isn't it? So if this has a certain sign, then px plus 28 has got married to the same sign, right? So far so good, right? Now let me examine the values of x for which this is positive, examine the values of x for which this is negative, this expression 12 minus 4x minus x squared. Okay. Now 12 minus 4x minus x squared is actually x plus 6 2 minus x. Yes or no? Yes or no? Right? Now realize that this could have been written as minus of x plus 6 into x minus 2. Right? Yes. If I had to just draw the wavy curve for x plus 6 into x minus 2. If I had to draw, that means wavy curve will tell me the sign of this expression in various intervals with nodes being minus 6 and 2. The wavy curve for this expression would be minus 6, 2, always to the right, it's going to be positive, and then it will alternate signs. This is the sign scheme for this expression in various available intervals, 3 intervals. Right? That's a wavy curve for this. Therefore, the wavy curve for this would be just the opposite, because there is a minus sign. Whatever is positive here will become negative. The whole thing will flip about this horizontal line. There will be a reflection of the whole thing about the horizontal line. The positives will become negative, the negatives will become positive, the positive will become negative. Right? So the wavy curve for this expression, which is minus 6, 2, this is the wavy curve. Minus here, plus here, minus here. This was the sign of 12 minus 4x minus x squared in various intervals. Yes or no? It's positive in the interval minus 6 to 2, negative to the right of minus 2, right of 2, and negative to the left of minus 6. Right? So So what we want is, of the two roots of this, one root lies in the interval minus 6 to 2, and the other root either lying to the right of 2 or lying to the left of minus 6. The root of this which lies to the right of 2 will cause this expression to be negative and therefore can be dumped. Right? A root of this which lies to the left of minus 6 and therefore causes this expression to be negative can also be discarded. Right? So then, for this quadratic, let me examine situation 1. The graph of this will be an upward opening parabola. The graph of this, because coefficient of x square is plus 1, the graph of this is an upward opening parabola. Now, refer to points minus 6 and 2. The graph of this, the parabola could have been like this. With one root x1 lying between minus 6 and 2, the other root not lying in the interval minus 6 to 2, the other root x2, let's say, to the right of 2. That could have been the graph of this parabola. One root lying between minus 6 to 2, the other root not lying between minus 6 to 2. It could lie either to the right of 2, one case, or the second case that we will examine after this would be the root lying to the left of minus 6. So this has two roots, good enough. But this equation will have only one root, x1. Why? Because only x1 will cause this expression to be positive. Yes or no? Okay, let me find the values of p for which the quadratic assumes this kind of a shape, this kind of a disposition in the plane. Okay, let me find. But I hope all of you are there with me. Any value of x obtained from this quadratic lying in the interval minus 6 to 2 will cause this expression to be positive and therefore would be looked upon as a legal root. A root not lying in the interval minus 6 to 2 will cause this expression to be negative. For example, x2 here, despite being a root of this, could not be looked upon as a solution to this because it will cause this expression to be negative and therefore can be rejected. Therefore, two roots of this quadratic, but only one solution to the logarithmic equation. How about it? Have I confused you? No. Now, very clearly then, for this would be y equal to f of minus 6. This length would be y equal to f of minus 6. This is the y direction. I am not unnecessarily drawing. This would be, for this point on the parabola, this would be f of minus 6. And this would be f of 2. Right? Yes or no? So what we must have is f of minus 6 greater than 0 and f of 2 less than 0. Yes or no? F of minus 6 greater than 0 and f of 2 less than 0. And means both conditions. It's not or, it's and. Both must hold good. Right? Yes or no? Now, f of minus 6. F of minus 6 I'll obtain from here. F of minus 6 is what? 36 minus 6 into p plus 4. This condition. 36 minus 6 into p plus 4 plus 16 greater than 0. Right? That would mean 6 into p plus 4 greater than, less than 52, or p plus 4 less than 26 by 3, right? Or p less than 14 by 3. Yes or no? P less than 14 by 3. Isn't it? So one thing, this gives me f of minus 6 greater than 0 gives me p less than 14 by 3. Yes or no? Right? Now, f of 2 less than 0. Can I wipe this off now? Or let me allow it to stay there. f of 2 less than 0. I need some room here. F of 2 less than 0 means 4 plus 2 into p plus 4 plus 16 less than 0. That's f of 2 less than 0. 4 plus 2 into p plus 4 plus 16 less than 0. Right? So that gives me 2 into p plus 4 less than minus 20. This gives me p plus 4 less than minus 10 or p less than minus 14. Yes or no? Right? So this gives me p less than minus 14. No, that's another case we will examine. That's why I said case 1. This is one possibility. I'm exploring all possibilities. Therefore, otherwise why would I at all marked it 1? Because I have more cases to talk about, right? So if this is the profiling of the parabola, then p less than 14 by 3 and p less than minus 14. If I combine these two conditions, then what's the condition? P less than minus 14. If this has to be true and this has to be true, that means p less than minus 14 has to be true. So these two conditions reduce to p less than minus 14. Right? Now, let me examine more things. P less than minus 14. Clear? So far, so good, right? Please ask questions.
Sir, would it f of 2 less than 0 would be self-sufficient, as you told earlier, to a number to lie between two roots?
No, f of 2 less than 0, how will that guarantee f of minus 6 greater than 0? All that, see, the fact that at one point it's positive and at another point it's negative will guarantee one real root. And if one real root is guaranteed, the second real root is also guaranteed. These two conditions together will guarantee one real root. And the moment a quadratic with real coefficients has one real root, it must have a second real root also. Because in order to go from a positive value to a negative value, it must pay tribute to the x-axis. And therefore guarantees one real root. But a quadratic with real coefficients can't have just one real root. If it has one real root, then it must have a second real root. And therefore, while exploring these conditions, I have not even looked at discriminant greater than 0. Why? Because that's built into this. If there is a change of sign, then two roots are guaranteed. And therefore, discriminant greater than 0 would be a redundant entity to explore. Weber, are you okay with this? Now, case 2. Case 2. Minus 6 to 2. Minus 6 to 2. Legal root. One that lies in the interval minus 6 to 2 will be a legal root. The one that doesn't lie in the interval minus 6 to 2 would be an illegal root. Will be a solution to the quadratic but not a solution to the logarithmic equation. Right? This is another possibility. Now the conditions for this parabola would be, this is minus 6, f of minus 6, this is f of minus 6, which must be less than 0. Right? And f of 2 must be greater than 0. F of 2 will be here on the parabola. F of 2 must be greater than 0. So this condition tantamounts to f of minus 6 less than 0, f of minus 6 less than 0, and f of 2 will be greater than 0. Yes or no? Now, I don't have to, again, like an idiot, do things here. If f of minus 6 greater than 0 has given me p less than 14 by 3, then f of minus 6 less than 0 will give me p greater than 14 by 3. Yes or no? Huh? So this will give me p greater than 14 by 3. And in this case, f of 2 less than 0 gave me p less than minus 14. F of 2 greater than 0 will give me p greater than minus 14, right? Is that okay or not okay? P greater than minus 14. Now, this condition and this condition will give me p greater than 14 by 3. So this is yes or no, right? That's case 2. Again, here also I didn't have to explore discriminant greater than 0 because a change of sign in the parabola has done that job for me. Discriminant will have to be non-negative if this happens, right? Okay. Now I have more cases to talk about. Everything. उसके पहले भी और सारा है, right? Now this I understand. See, remember this. Any root of the quadratic that lies in the interval minus 6 to 2 will be a legal root. At minus 6, this expression will be 0. If, let's say, for example, one root of the quadratic is minus 6, then that will cause this expression to be 0 and will be a illegal root. If this quadratic has a root 2, then this expression will become 0 at x equal to 2, and therefore, being a root of this quadratic will not be a root of this logarithm, because that will cause this expression to be 0. Log of 0 is undefined, right? So only those values of x that strictly lie between minus 6 to 2, to the exclusion of minus 6 and 2, can be looked upon as sanguine roots, right? So I reiterated that because I wanted to remove this. Okay, can I remove this and explore the next case? Case 3. Let's see if there is a value of p that will do this. Say this quadratic gives me one root as minus 6 and the other root legal lying between minus 6 and 2. This quadratic gave me two roots, one root minus 6 which will not be a legal root. X1 will be a legal root. This is x2 which is a root of this quadratic. Alright, this is also a possibility, but cannot be a root of this. Why? Because at x equal to minus 6 this will become 0. Right? So this case is also legal if there are values of p that subscribe to this condition, this positioning of the parabola, then those values of p can also be embraced. Right? Now, this is a case where one root of this quadratic is minus 6. Let me see if the second root lies in the interval minus 6 to 2. Now the product of the roots of this quadratic is 16. No matter what p is, the product of the roots of this quadratic is always 16. Yes or no? C by A. And if one root is minus 6, say x1 is, x2 is minus 6, then x1 would be minus 16 by 6. Yes or no? Yes or no? That is minus 8 by 3. Now, does minus 8 by 3 lie in the interval minus 6 to 2? Does minus 8 by 3 lie in the interval minus 6 to 2? Yes. So this can happen. This can happen. This can actually happen. One root which is minus 6. The other root, because of product of the roots being 16, turns out to be minus 8 by 3, which lies in the interval minus 6 to 2. x2 minus 6, x1 lying between minus 6 and 2. Siddharth, got me now? No. So, this root, a root of the quadratic, alright. but not a root of the logarithmic equation, because at x2 equal to minus 6, this will become 0. Therefore, only one legal root, x1, which is minus 8 by 3. Right, so this is an acceptable case. x1 equal to minus 8 by 3, x2 equal to minus 6 is an acceptable case. Right? Now, if these are the two roots, well, I can find the value of p, because sum of the roots is minus of p plus 4. Yes or no? Sum of the roots is minus of p plus 4. That's the sum of the roots. And that must be x1 plus x2. That must be x1 plus x2. Right? x1 plus x2 meaning x1, which is minus 6, x2 meaning minus 8 by 3. Right? Right? In fact, I'll tell you one thing. This is as if f of minus 6 is equal to 0. See, it's as if f of minus 6 is 0. I don't have to do this actually. Coming back to this. This case is as if f of minus 6 is 0. Right? And f of minus 6 will be equal to 0 when p is equal to 14 by 3. Isn't it? So I don't want to do this unnecessarily. We'll save the trouble, because I've already done that in this. So that will give me p equal to 14 by 3. Yes or no? Nay? Lost now? What is this case? This is a case where f of minus 6 is 0. And this is possible. If one root is minus 6, the other root is minus 8 by 3. Did you understand that? And minus 8 by 3 lies in the interval minus 6 to 2, and therefore is not just a legal root of this quadratic, is also a legal root of this logarithmic equation. Minus 6 is a legal root of the quadratic, but is not a legal root of the logarithmic equation. Why? Because at x equal to minus 6, this becomes 0. Right? Therefore, if I can find the value of p which gives me roots disposed as shown, then that value of p is fine. So now in this case, what happens? F of minus 6 is 0 now, because minus 6 is a root of this quadratic. F of minus 6 is 0. If f of minus 6 is greater than 0, I get p less than 14 by 3. But in that inequality, if I had put f of minus 6 equal to 0, then I would have got p equal to 14 by 3. Right? So this gives me p equal to 14 by 3. Good and acceptable. Good and acceptable. Right? Next possibility. Yes, 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 absolutely. One of the roots is 2, and the other root lying between minus 6 and 2. Let me see if that can happen. Right? Let me see if this can happen. One of the roots 2, and the other root, say one of the roots 2, which is an illegal root, x1, which is a legal root. Let me see if this can happen. That means in this case f2 is 0. So what's the if one root is 2, what about the other root then? 8. The other root is 8. Yes or no? So if x2 is 2, then x1 must be 8. Why? Because product of the roots is 16. Now this is not, 8 does not lie in the interval minus 6 to 2. 8 does not lie in that, because at least one root must lie in the interval minus 6 to 2. So that, you know, this logarithm can be defined. So this is a case where if one root of the quadratic is 2, the other root does not lie in the legitimate interval, because the other root turns out to be 8, which is not lying in the interval minus 6 to 2. Clear? Yes or no? Yes. Therefore, this case is grossly rejected. This case is grossly rejected. Right? Another case then. Okay. Where x1 equal to x2, discriminant equal to 0, right? Fourth case, fifth case. Right? Let me see if this is possible. x1 equal to x2. x1 x1 equal to x2 will happen for p equal to 4 or p equal to minus 12. So these are two more values of p that I will have to examine. x1 equal to x2 will happen for p equal to 4 or p equal to minus 12, right? Now, when p is 4, for example, let me see if p is 4 is acceptable. When p is 4, what is sum of the roots? Minus 8. That's sum of the roots? Minus 8, yes or no? Yes, p plus 4, minus of p plus 4 by 1, right? So p plus 4 then will become 8, minus of p plus 4 will become minus 8. That means sum of the roots is minus 8. That means each root must be minus 4. Yes or no? Both roots are equal. Sum of the roots, see, sum of the roots, say x1 plus x2 is minus 8, and since both roots are equal, each root must be minus 4. Now, does minus 4 lie in the interval minus 6 to 2? Yes. So this value of p is good. This value of p is good. It gives me two coincident roots of this quadratic lying in the interval minus 6 to 2 because it's minus 4, and two coincident roots means one solution. The solution is minus 4. Two coincident roots but one solution. So this happens for p equal to 4. P equal to 4 therefore can be accepted. The last, p equal to minus 12. Let me examine p equal to minus 12. Now p equal to minus 12, right? P equal to minus 12 means sum of the roots is minus 8, plus 8. That means each root is 4. But does 4 lie in the interval minus 6 to 2? 4 does not lie in the interval minus 6 to 2. 4 lies here. The parabola will look like this. Therefore, now this time this quadratic has no roots lying in the relevant interval minus 6 to 2, and therefore this value of p can be discarded. Yes or no? Right? Now let's consolidate all the conditions. We have exhausted all the conditions, right? You understand everything that I have communicated on this, right? Why don't you keep telling me the various conditions for 1, 2, 3, 4, 5? What did 1 give me? P? Less than minus 14. Okay. And or. Because either it will be this case, or case 2, or case 3, or case 4. So this is union. Whenever there is an or, it's a union. 1 or union or p equal to 14 by 3. So what I do is greater than or equal to 14 by 3. And then fourth case, which is now third for us, p equal to 4. This is all, right? So how you want to write this is p less than minus 14 means now p belongs to minus infinity to minus 14 not included. Union, there is a value, isolated value of p, which is 4. So that isolated value you write like this, 4 union p greater than or equal to 14 by 3. That means 14 by 3 to infinity. These are values of p that will give you a single solution to this equation. This one problem is like one full sheet. But it gives you quick, not that quick, it gives you exposure to all things that we have learnt in quadratics, right? Okay. Problem 2. Find all numbers A, find all values of the parameter A, for which the quadratic trinomial fx, which is 4x squared minus 4ax plus a squared minus 2a plus 2. In the interval, this quadratic has different values in different intervals. Now, in the interval x greater than or equal to 0, less than or equal to 2, the least value of this should turn out to be 3. That means in this interval, it has different values for different x's. The least value that this quadratic assumes in this interval, that means in this interval, the least value of this expression must be 3. We want to figure out values of a for which in the interval 0 to 2, the least value of this expression is 3. Okay? Now, 3 terms. A quadratic expression, it's a trinomial 3 terms. One x square term, x term, and the constant term. That's a quadratic trinomial. Right? Now, realize that this quadratic y equal to fx equal to ax squared plus bx plus c. Let's say if a is positive, then it's going to be an upward opening parabola, right? This quadratic always has an axis of symmetry, which is x equal to a by 2. X equal to a by 2 is the axis of symmetry. I'm sorry. Minus b by 2a. I'm so sorry. X equal to minus b by 2a will be the axis of symmetry. Actually, I looked at this and commented about that. This will have x equal to a by 2. See? Minus of this divided by twice of this, that would be x equal to a by 2. So, this has an axis of symmetry x equal to minus b by 2a. All of you understand this. Okay? Now, the interval 0 to 2. This is x equal to 0. This is x equal to 2. The axis of symmetry of this parabola, this is an upward opening parabola, y equal to fx equal to this. A is positive, so it's going to be an upward opening parabola. The axis of symmetry of this is going to be x equal to minus of this divided by twice of this. That means x equal to a by 2. X equal to a by 2 would be the axis of symmetry of this. Right? Now, as far as the interval 0 to 2 is concerned, right, the axis of symmetry based on what A is. Based on what A is, the axis of symmetry could either be to the left of 0, or could be between 0 and 2, or could be to the right of 2, and could also coincide with 0 and could coincide with x equal to 2. Right? But let me first explore the axis of symmetry to the left of 0, between 0 and 2, and to the right of 2. Right? Now, when the axis of symmetry is to the left of 0, then this will be the looks of the parabola. This will be the looks of the parabola, right? When the axis of symmetry, so this is case 1, is to the left of 0.
So, what will,
Huh?
so it's greater than or equal to 0, so why are we going to
What?
know the value of x, right?
I'm saying in this interval, this expression should assume a value least value 3. But it doesn't say anything about where the axis of symmetry lies. Why not? All that this says is that when you select values of x in the interval 0 to 2, then this expression should have a least value 3. What are the values of a that will cause that to happen? That's the problem. There is no commentary on a at all There are no limitations prima facie set on A, right? So for sure, if this is the disposition of the parabola, if this is the disposition of the parabola, then A by 2 is less than 0, right? A by 2 is less than 0. So A must be less than 0 for sure. A must be less than 0 for sure. Now, do you realize that if this is where the axis of symmetry is, then if you take the interval 0 to 2, it's continuously increasing from x equal to 0 all the way to 2. Fx is continuously increasing, therefore the least value would be at 0. F0 will be 3 therefore. F0 must be 3 therefore in this case. No. See? Zero, 2, this is the parabola, x equal to A by 2, right? If this is the axis of symmetry, then A by 2 must be less than 0. So A less than 0 for sure, right? Now in the interval 0 to 2, tell me, at what point does it assume the least value? At x equal to 0, isn't it? The function assumes the least value at x equal to 0. That means this length must be 3. That's what the problem says. No matter where it assumes the value 3, the least value in the interval 0 to 2 must be 3. The least value of fx in the interval 0 to 2 must be 3. And if this is the disposition of the parabola, then the least value is assumed at 0. F0 must be 3, yes or no? Yes, F0 must be 3. Right now? F0 and A less than 0 for sure. A less than 0 for sure. So in this case, case 1, A less than 0 and F0 equal to 3 and F0 equal to 3. Now F0 equal to 3 would mean what? Put x equal to 0. 0, 0, A squared minus 2A plus 2 must be 3, right? Right? Or A squared minus 2A minus 1 must be 0. Right? Yes or no? Sure. Or A must be minus B plus minus. If I solve for A, right? This gives me 1 plus minus root 2. Now, A has to be less than 0 and A has to be 1 plus minus root 2. Now 1 plus root 2 gives me A greater than 0. So 1 plus root 2 can be rejected. A therefore must be 1 minus root 2. A must therefore be 1 minus root 2. Yes or no? So one acceptable value of A is A equal to 1 minus root 2 for this situation. Right? Now, that's case 1. Case 2. Because if the axis of symmetry is to the left of 0, then A by 2 must be less than 0. So A has to be less than 0. So 1 plus root 2 is greater than 0. Therefore 1 plus root 2 is not accepted. Right? Now the second configuration of the parabola, when the axis of symmetry lies between 0 and 2. When the axis of symmetry lies between 0 and 2, right? This is x equal to A by 2, the axis of symmetry, lying between 0 and 2, right? So then, for x equal to A by 2 to lie between 0 and 2, this must be less than 2 and must be greater than 0. That means A must be greater than 0 and less than 4. That's one requirement. That's one requirement. That will only guarantee that the axis of symmetry lies in the interval 0 to 2. That's the only thing that it does. But then there is more it has to do. In the interval 0 to 2, the various y's that you get, of those y's, the least y should be 3. The least y should be 3. Now in this case, can you tell me at what value of x do you get the least value? At x equal to a by 2. Yes or no? This is the least value of the function. In the interval 0 to 2, the least value of the function is this. And that occurs at x equal to a by 2. So then this is like f of a by 2 must be equal to 3. So a must lie between 0 and 4 and f of a by 2 must be equal to 3, right? Let me see what this gives, right? So f of a by 2 equal to 3 means this is a square by 4. So this will simply become a squared. So a squared minus 4a squared minus 2a squared plus a squared minus 2a plus 2 must be equal to 3. Yes or no? That gives me 2a equal to minus 1 or a equal to minus half. Now, a greater than 0 and less than 4 and a equal to minus half. Can you find any common value of a? That means this case is rejected. This is not possible to satisfy, or this will never satisfy the given bunch of conditions. Because on one hand, the axis of symmetry lies in the interval 0 to 2 and the least value equal to 3 at a by 2 therefore will give me a equal to minus half, which does not subscribe to this condition. Therefore, this case can be rejected. Right now?
Why are you taking the discriminant less than 0 each time?
No, I am not taking, I have not even used that. It's just that I have drawn the figure this way, but I have not used that anywhere. Have I used that anywhere? Then it does not matter. I have not used discriminant at all in this situation. Right? I have just made sure that the least value in the interval 0 to 2 while drawing the graph doesn't fall below the x-axis, because that must be equal to 3 positive number. So that's the only thing that I have ensured in my attempt to draw the graph. Right? Third possibility, when the axis of symmetry moves to the right of 2. Right? So this case anyways is rejected. Right? Case 3. This becomes the parabola with its axis of symmetry x equal to a by 2 to the right of 2 means greater than 2. That means a greater than 4. Not just that. Now tell me, in the interval 0 to 2, at what point does it obtain the least value? At x equal to 2. See, at 0 it's this value and then it keeps decreasing. The least value in the interval 0 to 2 is at x equal to 2. Yes or no? So this must be f2 equal to 3. f2 equal to 3. Let me find the value of a for which f2 is 3. f2 is 3 means 16 minus 8a plus a squared minus 2a plus 2 equal to 3. Right? This gives me like a squared minus 10a plus 15 equal to 0. Which then reduces to a equal to plus minus 100 minus 60 40 divided by 2, right, which gives me 5 plus minus root 10. But a has to be greater than 4. So, but 5 minus root 10 is not greater than 4. Therefore, the only value of a that is acceptable is 5 plus root 10. 5 plus root 10. So, this case gives me a equal to 5 plus root 10. This case gave me a equal to 1 minus root 2. Right?
So if the parabola dips below that line, then
The least we want to be positive, right?
No, but the positive least in that case. Suppose like you have this thing, so this is the least thing.
So what? No, the least then will be the negative number. Will not be a positive number. Least when then would be a negative number.
Okay, so we are seeing it that way.
Yes.
We cannot take like the positive least.
No, 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 no. So far so good, right? Huh? Two cases I will leave to you to explore. One, where the axis of symmetry coincides with x equal to 0, which will cause a by 2 to be 0 and therefore a to be 0. Right? The second case where the axis of symmetry x equal to a by 2 would coincide, that means a must be 4, a by 2 must be 2, a therefore must be 4. Now, will a equal to 4 do the trick for us, or will a equal to 0 do the trick for us? You will have to, I want you to do independently. Right? But by and large, again, you understand how to play around with graphs. I also hope you understand why I did not touch on quadratics when you came to me in the beginning of class 11 and you were hitting on me so hard to teach you quadratics right then and there. If I had taught quadratics the way it should be taught, the way it is, then you would have wanted to move to commerce. No, I mean, it's not about sum of roots and product of the roots, which you anyways knew in class 9, 10, or some of you earlier than that. But, you know, there is semblance of maturity that you require in terms of dealing with expressions, in terms of understanding a few more things in mathematics, some more tools. In fact, even now, I would say that I have given you a semi-baked feel for quadratics. The real thing would come when I actually deal with more of calculus, when I take you into the thick of calculus. That's when I'll be able to give you the true nicety of, you know, parabolas, quadratics, etc. But again, you know, this would be a good starting point at least for our digressions on parabolas, quadratics, etc. Okay. Let me look at 3. The equation x power nx, x power n plus px squared plus qx plus r equal to 0, where n is greater than or equal to 5 and r not equal to 0. It has roots alpha 1, alpha 2, alpha n, and sk is defined as summation alpha I to the power k, I equal to 1 to n. That's sk. We want to show that all alpha i's can't be real. We want to show that all alpha i's can't be real. That's the first part of the problem. Some can be real, but not all. Not all the roots of this equation can be real. That's what we want to prove. Now, suppose all are real. Suppose all are real. Let's move to the method of contradiction, right? Say all are real. Now, sum of the roots alpha 1, alpha 2, alpha 3, alpha n is 0. Because coefficient of x power n minus 1 is 0. Coefficient of x power n minus 1 is 0. So, sum of the roots is 0. Also, look at this. Product of the roots alpha 1, alpha 2, alpha 3, alpha n is minus 1 to power n r. Is minus 1 to power n. Sum of the product taken n at a time is minus 1 to power n. Last term divided by coefficient of first term, right? Now r is not 0. That's given. It's given in the problem. R is not 0 somewhere. R is not 0. If r is not 0, that means the product of the roots is not 0. That means no root can be 0. No alpha I can be 0. Yes or no? Because even if one alpha I is 0, that will cause the product to be 0. Right? So, no alpha I is 0. No alpha I is 0. Right? This is the product of the roots. Huh? I'm saying if even one alpha I was 0, then the product of the roots would have become 0, and that would have caused r to be 0, but r is not 0. If the product of the roots is not 0, then no root can be 0, isn't it? So no alpha I is 0. Is it not? No alpha I is really 0. Now, sum of the product taken 2 at a time, which is in brief written as alpha 1, alpha 2. Alpha 1, alpha 2, alpha 2, alpha 3, alpha 3, alpha 1, which has NC2 terms in this summation. Summation alpha 1, alpha 2 means sum of the product taken 2 at a time. Now, there will be coefficient of x bar n minus 2 divided by 1. So that's also 0, because coefficient of x bar n minus 2 is also 0 here, right? Right? Yes or no? So that is S2. Let me call it sum of the product taken 2 at a time. Now, can I say the following? Alpha 1 plus alpha 2 plus alpha n whole squared is alpha 1 squared plus alpha 2 squared plus alpha n squared plus twice S2, twice sum of the product taken 2 at a time, 2 times alpha 1, alpha 2, alpha 2, alpha 3, alpha 3, alpha 1, those kind of terms, yes or no? Yes, now this is 0, alpha 1 plus alpha 2 plus alpha n is 0, S2 is 0, no? Therefore, alpha 1 squared plus alpha 2 squared plus alpha n squared must be 0, huh? This would mean that alpha 1 squared plus alpha 2 squared plus alpha n squared is 0. But all roots are real. And therefore these are non-negative real numbers. Non-negative real numbers adding up to 0 is possible when each of the alpha i's is 0. This will happen when each alpha I is 0, yes or no? But no alpha I is 0. But no alpha I is 0. Therefore this is not possible for all real alpha i's. If alpha i's were all real, this would be non-negative, this would be non-negative, this would be non-negative, non-negative, adding up to 0. If sum of several non-negative real numbers add up to 0, then each must be 0. This will mean that each alpha I must be 0. Each alpha I must be 0, because alpha i's are real, right? But alpha I is not 0. So this case is not possible. So this equation cannot have all real roots, yes or no? Yes, sir. Therefore, so that's part 1 of the problem. That's part 1 of the problem. So far so good, right? Can I wipe this off? Part 2 of the problem, Sn is minus Nr. Sn is minus Nr. What is Sn? Sn is actually alpha 1 to power n plus alpha 2 to power n plus alpha 3 to power n. Instead of k you have n, right? That means we want to show that alpha 1 to power n plus alpha 2 to power n plus alpha 3 to power n plus alpha n to the power n is minus Nr. That's what we want to show. Put k equal to n in this, you get, right? Now alpha 1, alpha 2, alpha n are all roots of this equation, are all roots of this equation, and therefore will satisfy this equation, yes or no? Yes, so if alpha 1 satisfies this equation, then alpha 1 to power n plus p times alpha 1 squared plus q times alpha 1 plus r must be 0. Alpha 1 to power n plus p times alpha 1 squared plus q times alpha 1 plus r must be 0. Same for alpha 2, same for alpha 3, same for alpha 4 and alpha n and so on and so forth, right? Alpha 2 to power n plus p times alpha 2 squared plus q times alpha 2 plus r is 0. And going this way, alpha n to power n plus p times alpha n to power n alpha n squared plus q times alpha n plus r must be 0, right? Add all of this. This will be Sn. If I add all of this, this will be Sn, yes or no? This plus this plus this will be Sn plus p times alpha 1 squared plus alpha 2 squared plus alpha n squared, which is 0 anyways, established, 0 plus q times alpha 1 plus alpha 2 plus alpha n, which is also 0. And then r n times would be nr, that must be 0. Sn therefore is minus nr. Huh? If alpha i's were all real, but alpha i's are complex, then alpha I squareds can be negative also. For example, if alpha I is 2i, 2 times the imaginary number I, then square of an, right? Yes. Only if alpha i's were real, but not all alpha i's are real. Right? Is that okay or not? Okay. Now I think I would leave you with some time to, spend on the problems independently. So have an independent excursion for a while with the remaining problems, and I'll keep hopping in and solving stuff for you, right? We want to find all positive real numbers. Hello, hello. We want to be able to find all positive real numbers satisfying minus 6. Minus 1 is not positive, right? And how do you know there are, huh? By inspection, you can't say there aren't others. By inspection, you can only say this is a solution. How would you know by inspection? You are not God, that you would know there aren't others, right? That only God would know. Huh? Right? Therefore, we need something more than inspection. Good. By inspection, 1 comma 1 is a solution to this equation. Now this equation is like x power 8, x and y are positive real numbers, right? Plus y to power 8 plus 6 is 8xy, yes or no? This is like x power 8, one number, y to power 8, another number, plus 6 ones divided by 8 equals 8th root of x power 8, y to power 8 into 1 into 1 into 1 6 times. There are 8 numbers, 1, 2, 3, 4, 5, 6, 7, 8. That's the arithmetic mean of the 8 numbers. 8th root of the product will be the geometric mean of the numbers. That means, this means that the arithmetic mean of these numbers is equal to the geometric mean of these numbers. That can happen only when the numbers are all equal. AM will be equal to GM only if the numbers are all equal. Yes or no? Yes. That means x power 8 will be equal to y power 8 equal to this one, equal to this one, equal to this one, equal to all ones. Each is 1, therefore x equal to y equal to 1. Much ado about nothing. Right? AM equal to GM. That's what this statement is. Numbers are all non-negative. AM will be equal to GM for non-negative numbers if the numbers involved in the constitution of AM GM are all equal. Right? Right? Number 5. Fx is a polynomial with integer coefficients. Fx is a polynomial with integer coefficients. Fx has integer coefficients. And it's given that f1 and f2 are odd integers. f1 and f2 are all odd integers, right? And fx does not become 0 for any integer n. If n is an integer, then fn cannot be 0. That means fx has no integer roots. It means fx has no integer roots. You know what I'm saying? It will not become 0 for an integer value of x. F of an integer is not 0. Fx has no integer roots, right? This is what we want to establish. Sorry, this is what we want to prove, that if this be the case, if fx has integer coefficients and f1 and f2 are odd numbers, then we want to establish that fx cannot be 0 for an integer value n, right? What I assume is, suppose fx becomes 0 for an integer n. Did you understand that fx has integer coefficients? The value of fx at 1 and at x equal to 2 are odd numbers. We want to prove that fx cannot be 0 when x is an integer. That means f of an integer is not 0. The value of this function at x equal to an integer cannot be 0. No, didn't understand this. No? Okay. Okay. Suppose, let's assume that fx has an integer root. X equal to n. That means fx becomes 0 at x equal to n, say. Let's assume that it has an integer root, n. Let's say fx does become 0 at an integer value of x, say n. That means if fx is becoming 0 at x equal to n, that means x minus n must be a factor of fx, yes or no? And when you factorize something, you are producing an equation or an identity. Identity, right. That means fx must have a factor x minus n. One of the factors must be x minus n, and fx therefore could be looked upon as x minus n into some g of x, into some other polynomial gx. If fx is a polynomial of degree t, then gx will be a polynomial of degree t minus 1. Yes or no? And if fx has all integer coefficients, then gx will also have all integer coefficients. Yes or no? So far so good, right? Now f1, f2. What is f1? 1 minus n into g1. Since gx has all integer coefficients, g1 will be an integer. Since the coefficient of different powers of x and gx are all integers, then if you plug in x equal to 1, you will get sum of several integers. So g1 will be an integer. g1 therefore is an integer. Right? f2. 2 minus n into g2. Similarly, g2 will also be an integer. Right? Now, f1 is an odd integer, f2 is also an odd integer. That's given in the problem. And we have assumed that fx has an integer root n. So we are actually adopting the method of contradiction, right? Now realize that 1 minus n and 2 minus n are consecutive integers, yes or no? 1 minus n and 2 minus n are consecutive integers, so one of them must be even, yes or no? Between 1 minus n and 2 minus n, one must be even, right? So that means between f1 and f2, one must be even. But it's given that f1 and f2 are both odd, so it leads to a contradiction. The problem therefore must be with the basic assumption that fx becomes 0 at x equal to an integer n. 1 minus n and 2 minus n, right? They are consecutive integers. So either this will be even or this will be even. One of them must be even. Either this is even or this will be even, which would mean either f1 even or f2 even. One of them must be even, but it's given that both are odd. So it led to a contradiction. Therefore the basic assumption that fx becomes 0 at x equal to an integer n must be incorrect. No? Fx therefore cannot become 0 at x equal to an integer. Confused kya? The entire thing? Okay. Now fx is a polynomial with integer coefficients, right? The value of the function at x equal to 1 at x equal to 2 is an odd number, right? We have to prove that fx cannot become 0 when x is an integer. Fx does not have integer roots. That's what we want to show. We assume in contrast that fx becomes 0 at x equal to an integer n. We assume that fx actually becomes 0 at x equal to n, right? Now if fx becomes 0 at x equal to n, then by remainder theorem x minus n must be a factor. Therefore fx could be identically written as x minus n into gx, where gx will be a polynomial of degree 1 less than fx, t minus 1, because this n, you know. Now f1 would be, put x equal to 1 on both sides, f1 would be 1 minus n into g1, f2 would be 2 minus n into g2. We actually want to show that this is not a possibility. X equal to n cannot be a factor of fx, right? We have assumed that it's a factor, right? Now 1 minus n and 2 minus n, are they not consecutive integers? See, this is one more than this. They're consecutive integers, isn't it? So one of them must be even. That means if one of them is even, then either f1 is even or f2 is even. But it's given that both are odd. It's given that both are odd. So that means it leads to a contradiction that one of them is even. No. And therefore the basic assumption must be wrong, that x minus n is a factor of fx, and therefore that x equal to n is a root of fx. Do you all understand this? In the next problem, problem 6, we want to show that a square plus ab plus b squared greater than or equal to 3 times a plus b minus 1 for ab belonging to the set of real numbers. If a and b are real numbers, we want to be able to establish this: a square plus ab plus b squared greater than or equal to this, right? Wonder what's the element of quadratic knowledge that you require to obtain this. Oh, okay. No rocket science really. This is as if and only if a squared plus b minus 3 into a, see, I transpose this, b minus 3 into a plus b squared minus 3b plus 3 greater than or equal to 0, we want to show that this is true, right? Let me think of this quadratic expression, the left hand side quadratic expression, y versus a. y. Instead of x, you have a here. Y versus a. The quadratic expression a squared plus b minus 3 into a plus b squared minus 3b plus 3. Let me look at this expression. First of all, y versus a is going to be an upward opening parabola. Why? Because coefficient of a squared is positive, right? It's going to be an upward opening parabola, right? Now, for this parabola, examine the discriminant. B minus 3 whole square minus 4 into b squared minus 3b plus 3. That's a discriminant, right? Which is like minus 3b squared minus 6b plus 12b. So plus 6b, 9 minus 12 minus 3. Yes or no? Right? Which is minus 3 into b squared minus 2b plus 1. Right? Which is minus 3 into b minus 1 whole square. Therefore, this is always less than or equal to 0. The discriminant of this quadratic is less than or equal to 0. That means the graph of this can have two possibilities. When discriminant less than 0, the y versus a, y equal to fa versus a, upward opening parabola with no real roots when this is less than 0, would be like this. No real roots. And in which case, for any given a, f of a would be greater than 0. F of a greater than 0. That's one possibility when the discriminant is less than 0. Yes or no? Yes, when discriminant is equal to 0, so this is discriminant less than 0. The other possibility, when the discriminant equals 0, upward opening parabola, discriminant equal to 0 means equal real roots. It will touch the a-axis in this case. This is discriminant equal to 0. In which case, for any given a, f of a will either be greater than 0 or f of a could be equal to 0. So this is the case where f of a greater than or equal to 0. Right? This is the case where fa greater than 0. This is the case where fa greater than or equal to 0. That is what happens. So when discriminant of this is less than or equal to 0, f of a must be greater than or equal to 0. Right? So this conclusion of out of this is f of a greater than or equal to 0, which is what we set out to prove. F of a greater than or equal to 0 is what we set out to prove. Right? There we go. Isn't it? Okay. You have not attempted problems after this. Okay. Start looking at 7 part 1. In part 2, just make a small correction. It's given x plus y plus z is a. Alright. It's given x squared plus y squared plus z squared is a squared. Make that b squared equal to b squared. And x cubed plus y cubed plus z cubed equal to a cubed. That's fine. So only the middle one, x squared plus y squared plus z squared, make that b squared instead of a squared. Okay. And start solving this system of equations. Seven part 1. X plus py plus p squared z is p cubed. X plus qy plus q squared z is q cubed. X plus ry plus r squared z is r cubed. Realize that there is structural similarity in these equations. They are all of the form x plus some ty plus t squared z equal to t cubed. They are all of this form, where t is p here, t is q here, and t is r here. Right? T can be p, q, or r. T is P, Q or R? That means, what are the roots of this equation? P, Q and R are the roots of this equation, right? That means t cubed minus t squared z minus ty minus x equal to 0 has roots p, q, r. This equation has roots p, q and r. Now, very clearly, then sum of the roots p plus q plus r is minus of minus z by 1. That means z. So we know z. Right? Sum of the product taken two at a time. That means pq plus qr plus rp would be minus 1 squared into minus y. So then y is known to us, right? Product of the roots pqr is minus 1 cubed into minus x. So that gives me x, this gives me y, this gives me z without any effort. Yes or no? Got me? I'll leave part 2 to you, but let me move to 8. Have you been able to do part 2 also? No? Okay. I wouldn't remember the answer, but one of the solutions, there are six solutions to this equation. You got 6 solutions? Then have fun. Let me look at 8 first. Okay, I would want you to think about 7 part 2 once again. Let me do 8 for you first. Polynomials was any different from what I was doing. You know, I was doing polynomials only all along. As a special case, quadratics is only a special case, and you know, sum of roots, sum of product taken 2 at a time, 3 at a time, that's all part of polynomials only. So when I said polynomials, I meant problem solving on polynomials. Now the entire gamut extends to generalized instead of staying confined to quadratics. So just a couple of remarks which might be handy, which you could have figured out independently as well. First of all, let me tell you that if there is a polynomial like this, px equal to say x minus 1 whole cubed into x plus 1 into some qx, right? Suppose this is a polynomial. Now, in this case, 1 is a root, minus 1 is a root. 1 is a root of multiplicity 3. That means it's a repeated root. 1 is a root because this could have been written as x minus 1 into x minus 1 into x minus 1. That would be counted as 3 coincident roots. It would be counted as 3 coincident roots. Then there is a root minus 1 and so on and so forth, right? So 1 is a root of multiplicity 3, or 1 is a root repeated thrice. That is what it means, right? So if there is a polynomial px, which is say x minus alpha to power k into some qx, then alpha will be a root repeated k times, where k can be 1, 2, 3, 4, etc. Then alpha is a root of multiplicity k. Now, an important result that emerges out of this, if px is a polynomial, p dash x is the derivative of px. P dash x is the derivative of px. Now that you can obtain from the product rule of differentiation. So that's going to be k into x minus alpha to power k minus 1 into qx plus x minus alpha to the power k into q dash x, right? Product rule of differentiation. Now from this, I could have taken x minus alpha to power k minus 1 common. So if I took x minus alpha to power k minus 1 common, then what I am left with in the parenthesis is k times qx plus x minus alpha times q dash x. Yes or no? Right? That's the derivative function. P dash x is the derivative function. Now, observe this. So, what it means is if alpha is a root of a polynomial of multiplicity k, that is repeated k times, then alpha will be a root of its derivative function of multiplicity 1 less or k minus 1. That means alpha will be a root repeated k minus 1 time. Right? So if there is a root alpha repeated twice in a polynomial, then its derivative, it will be repeated once. If alpha is a root repeated 4 times in a function, that is of multiplicity 4, then its derivative will have alpha as a root repeated thrice, 3 times. Right? Now this is important to understand. Now, what that means is, look at the first problem. Look at the first problem. Double root means a root repeated twice. Double root means a root repeated twice. That means a root of multiplicity 2. A root of multiplicity 2. That's what it means. Now the first problem, that is the 10th problem of the sheet titled Ollie Poly. If unity is a double repeated root, that means is a root repeated twice for a polynomial fx, which is given as px cubed plus q into x squared plus x plus r. If fx is a function with a root x equal to 1 of multiplicity 2, that means repeated twice, then 1 will be a root of its derivative repeated once. That means if 1 is a root of this, 1 will also be a root of its derivative. 1 will also be a root of its derivative. Yes or no? Right? Okay. Now, which means if 1 is a repeated root of fx, f of 1 must be 0. F of 1 must be 0. Yes or no? Right? Which would mean p plus 2q plus r must be 0. How about it? X equal to 1, p plus 2q plus r must be 0. Now, 1 is also a root of its derivative, repeated once, right? So, f dash x is 3px squared plus q into 2x plus 1, that's f dash x. F dash 1 will be 0 because 1 will also be a root of the derivative function repeated once, right? So f dash 1 will be 0, which means 3p plus 3q must be 0, right? Which means p must be equal to minus q. P must be equal to minus q. Now, if you plug in p equal to minus q in equation 1, p equal to minus q, you get q equal to minus r. You get q equal to minus r, p equal to minus q, bless you. You get q equal to minus r, right? So we eventually have q equal to minus r, right? Which means p equals minus q equals r. Very clearly, p and q are of opposite signs. If p is minus q, p and q are of opposite signs. Yes or no? And if p and q are of opposite signs, pq must be less than 0. That's the only conclusion you can have. Pq must be less than 0. If p and q are of opposite signs, pq must be less than 0. P equal to minus q, therefore pq must be less than 0. What do you say? Right? All's good? Can I wipe this off? $11. Abe, yes. Why D? That's my question. All that I know is PQ is less than 0. But do I know the sign of R? Nothing conclusive could be said about D. Obviously, yaar. There are only two signs produced by mankind. Either it has to be greater than 0 or less than 0. So now, that's all right. You know. Now, in the next problem, A, B, C are real numbers. That's given. A not equal to 0. And we will also assume that C is not 0. Alpha, beta are the roots of ax squared plus bx plus c. Are the roots of this quadratic. We need to obtain the roots of a cubed x squared plus abc into x plus c cubed equal to 0. We need to obtain the roots of this. All right. Now, what I would be tempted to do here is, I would be tempted to write this quadratic in this form. That means I would want to write this as a into square of something plus b into something plus c equal to 0 is what I want to be able to do. Yes or no? So that, you know, there is a comparison index between these two equations. So I would want to make this c, isn't it? So that, you know, I have some reason to compare. So let me first divide by c squared so that I could make this c. So if I divide that by c squared, then a into a cubed into x squared by c squared plus ab into x divided by c plus c equal to 0. Right? Now I would want to write this as a into something plus b into something plus c equal to 0. Only because I could compare the two equations that way, right? So I would then want to write this as a into ax by c whole square, right? A into a square x square by c square, so ax by c whole square, right? Plus b into ax by c plus c equal to 0. Yes or no? But what's given is a into alpha squared plus b into alpha plus c must be 0. So this will be satisfied where if ax by c is alpha or ax by c is beta. Yes or no? This equation would be satisfied if ax by c is alpha or ax by c is beta, right? Which means ax by c equal to alpha beta would be the roots of this quadratic, right? But what is c by a? C by a is alpha beta, isn't it? C by a, the product of the roots, is alpha beta. C by a is alpha beta, right? So then, if you write c by a as alpha beta, then taking this as alpha, this I'll get x equal to alpha squared beta. If I take this equal to beta and write c by a as alpha beta, I get alpha beta squared, isn't it? If I write c by a as alpha beta, then alpha squared beta or alpha beta squared. Yes or no? Right? So the roots, the two roots of this quadratic would be alpha squared beta or alpha beta squared. Clear? See, if there is a polynomial a naught x power n plus a1 x power n minus 1 plus a2 x power n minus 2 plus an. Suppose this is a polynomial, right, of degree n and x. It will have exactly n roots, real or complex, distinct or coincident, right? Its roots would be say alpha 1, alpha 2, alpha 3 and alpha n would be the roots of this polynomial of degree n and x, right? Suppose I want to translate this into a polynomial. We want to find a polynomial whose roots are alpha 1 plus h, alpha 2 plus h, alpha 3 plus h, alpha n plus h. That means when I solve for x, I get these as the roots. Suppose I want to find a polynomial whose roots are alpha 1 plus h, alpha 2 plus h, alpha 3 plus h, alpha n plus h. Right? Now, what I do is, I create a transformation of this kind. Y equal to some x plus h. Let me create a transformation of this kind. Y equal to x plus h. Now, very clearly, when x is alpha 1, what is y? Alpha 1 plus h. When x is alpha 2, what is y? Alpha 2 plus h. When x is alpha 3, what is y? Alpha 3 plus h, and so on and so forth, right? So the various values of x that emerge are alpha 1, alpha 2, alpha 3, alpha n. Then the various values of y that would emerge would be alpha 1 plus h, alpha 2 plus h, alpha 3 plus h, alpha n plus h. Yes or no? Now, if I create this, that means if I replace x by y minus h in this equation, if I replace x by y minus h in this equation, then the various values of y that I would get would be alpha 1 plus h, alpha 2 plus h, alpha 3 plus h, alpha n plus h. Yes or no? Those would be the various values of y that we get, right? Clear? So, this polynomial on replacing x by y minus h would give me a naught y minus h to the power n plus a1 y minus h to the power n minus 1 plus a2 y minus h to the power n minus 2 plus an. Yes or no? So if this equal to 0 is satisfied by alpha 1, alpha 2, alpha 3, alpha n, then this would be, when you solve for y, the values of y that would be obtained would be alpha 1 plus h, alpha 2 plus h, alpha 3 plus h, alpha n plus h would be the various values of y that would emerge out of solving this. So what would be the roots of this equation? What would be the roots of this equation when you solve for y? Because see, y minus h could be alpha 1, or y minus h could be alpha 2, or y minus 3 h could be alpha 3, or y minus h could be alpha n. So y, when you solve for y would be alpha 1 plus h, alpha 2 plus h, alpha n plus h, and so on and so forth. So when I expand this and coagulate terms, then the solution in y would be alpha 1 plus h, alpha 2 plus h, alpha n plus h. Yes or no? Now, if I replace y by t and solve for t, what would be the roots? Alpha 1 plus h. If I replace y by p and solve for p, what would be the roots? If I now replace y by x, what would be the values of x? Alpha 1 plus h, alpha 2 plus h, alpha 3 plus h, alpha n plus h. Yes or no? Now, just to bring about uniformity in symbolism, what I do is, since this is a naught x minus h to power n plus a1 x minus h to power n minus 1 plus an equal to 0, the various values of x minus h that you would get would be alpha 1, alpha 2, alpha 3, alpha n. So the various values of x that you would get would be alpha 1 plus h, alpha 2 plus h, alpha n plus h. Yes or no? So this transformation would give me roots that are alpha 1 plus h, alpha 2 plus h, alpha n plus h. Yes or no? Clear? So now, once you understand this, clear? Suppose I want a transformation of the following kind. I want the roots to be alpha 1 plus 1 by alpha 1 minus 1, alpha 2 plus 1 by alpha 2 minus 1, alpha n plus 1 by alpha n minus 1. Suppose I want a polynomial whose roots are these: alpha 1 plus 1, alpha 1 minus 1, alpha 2 plus 1, alpha 2 minus 1, alpha n plus 1, alpha n minus 1. Suppose I want a polynomial whose roots are these instead. Then what I do is, I create a transformation y equal to x plus 1 by x minus 1 using this template. X plus 1 by x minus 1 is the transformation that I generate. Now, every time when you solve for x and x turns out to be alpha 1 plus 1 by alpha 1 minus 1, I'm sorry, every time x turns out to be alpha 1, y turns out to be alpha 1 plus 1 by alpha 1 minus 1. If x turns out to be alpha 2, the second root, then y will be alpha 2 plus 1 by alpha 2 minus 1. If x is alpha n, y will turn out to be alpha n plus 1 by alpha n minus 1. Yes or no? So in this transformation, if you write this equation in terms of y and solve for y, then the roots in y obtained would be these. These would be the roots obtained in y. If you write the whole thing in terms of y, yes or no, then these would be the roots. So then, to write this in terms of y very clearly, I could write this as x into y minus 1 is 1 plus y. So x then turns out to be y plus 1 by y minus 1. X then turns out to be y plus 1 by y minus 1. Yes or no? Do you realize that? So let me replace x by y plus 1 by y minus 1. Right? So if I replace x by y plus 1 by y minus 1, so a naught y plus 1 by y minus 1 whole to power n plus a1 n minus 1 plus an equal to 0. Now if you solve for y, what would be the roots? These would be the roots in y. Right? If you replace y by t, what would be the roots? If you replace y by monkey, what would be the roots? Same. If you replace y by x and solve for x, then these would be the roots. Yes or no? So if I replace y by x, a naught x plus 1 by x minus 1 whole to power n plus a1 x plus 1 by x minus 1 whole to power n minus 1 plus an equal to 0, and if you solve for x, you would get these as the roots of the polynomial. Yes or no? Do you all subscribe to this? Huh? Now, no, you don't have to. You can maintain it in y and solve for y. You want to retain it like this and solve for y? Do you understand when I solve for y, I get these as the roots? Do you understand this? If I now replace y by q and solve for q, what would be the roots? These. No? Okay. Suppose there is a quadratic ax squared plus bx plus c equal to 0. Right? Suppose this is a quadratic and its roots are alpha beta. Alright. And now if there is a quadratic at squared plus bt plus c equal to 0, what would be the roots of this quadratic? Okay. Say 2x squared plus x plus 1 equal to 0. Suppose the roots are alpha beta. Right? Then 2y squared plus y plus 1 equal to 0. What will be the roots of this? Precisely. Got me? All's good? Suppose, I mean, this is just to, you don't have to replace y by x, you can solve for y instead, but just to maintain uniformity and homogeneity in the whole entity, we're doing this. But you can just go ahead with y itself. Suppose there I want a polynomial whose roots are 2 alpha 1 plus 3 by 5 alpha 1 minus 4, 2 alpha 2 plus 3 by 5 alpha 2 minus 4, 2 alpha n plus 3 by 5 alpha n minus 4. Suppose I want a polynomial whose roots are these. Then what's the transformation that I'll create? Y equal to 2x plus 3 by 5x minus 4. Right? You can solve for x in terms of y, write this polynomial in terms of y, and the various values of y that you would get would be these. Now if you replace those y's by x's, then the various values of x that you would get would be these. How about it? Right? You understand this business of transformation then? Very good. Now can I wipe this off? Suppose I want a polynomial whose roots are 1 by alpha 1, 1 by alpha 2, 1 by alpha 3, 1 by alpha n. Suppose I want a polynomial whose roots are these. So I'll create a transformation y equal to 1 by x. So every time x is alpha 1, y is 1 by alpha 1. X is alpha 2, y is 1 by alpha 2. So if I replace y equal to 1 by x and replace x by 1 by y here, then I get a naught 1 by y to power n plus a1 1 by y to power n minus 1 plus an equal to 0. Now if you solve for y, that means if you solve for 1 by y, you would get roots as alpha 1, alpha 2, alpha 3, alpha n. So if you solve for y, the roots would be 1 by alpha 1, 1 by alpha 2, 1 by alpha 3, 1 by. Now if you replace y by x, what would be the roots in x? 1 by alpha 1, 1 by alpha 2, 1 by alpha 3, 1 by alpha n. So which means this equation will, when you solve for x, would give you roots 1 by alpha 1, 1 by alpha 2, 1 by alpha 3, 1 by alpha n. So if you have a polynomial and you are seeking a polynomial whose roots are reciprocal of the given polynomial, then all that you need to do is replace x by 1 by x. Right? Suppose you want a polynomial. Can I wipe this off? Suppose you want a polynomial whose roots are minus alpha 1, minus alpha 2, minus alpha 3, minus alpha n. What's the transformation that you'll use? Y equal to minus x, y equal to minus x. That means x is minus y. So replace x by minus y. Now if you solve for y, what would be the roots in y? Minus alpha 1, minus alpha 2, minus alpha 3, minus alpha n. If you replace y by x and solve for x, you'll get the same roots, right? So a naught minus x to power n plus a1 minus x to power n minus 1 plus an equal to 0 will give you roots minus alpha 1, minus alpha 2, minus alpha 3, minus alpha n. So if there is a polynomial and you are seeking a polynomial whose roots are negative of those roots, then just replace x by minus x. Just replace x by minus x. You end up getting a polynomial whose roots are negative of the roots of the given polynomial. Yes or no? All of you understand this transformation? No issues with this, right? All right, then. Number 12. We have a cubic x cubed plus px plus q equal to 0 is a cubic whose roots are alpha, beta, gamma. Whose roots are alpha, beta, gamma. And we are seeking a cubic whose roots are alpha plus 2, beta plus 2, gamma plus 2. What's the transformation that you're going to perform? Y equal to x plus 2. So if x is alpha, y would be alpha plus 2 and so on and so forth, right? Yes or no, Saurav, right? So put x equal to y minus 2 here. So y minus 2 whole cubed plus p into y minus 2 plus q equal to 0. Now if you solve for y, you would get alpha plus 2, beta plus 2, gamma plus 2. Replace y by x, you get the same roots. So replacing x by x minus 2 in the mother equation, the task gets accomplished. It'll give you x minus 2 as, when you solve for x minus 2, you get alpha, beta, gamma. So x will be 2 plus alpha, 2 plus beta and 2 plus gamma. Right? Proceed. And you can simplify this and write it as another cubic, and that cubic would have roots alpha plus 2, beta plus 2, and gamma plus 2. You can cube all of this and simplify matters here. Alpha plus I beta, alpha and beta are real numbers, is a root of the cubic x cubed plus qx plus r equal to 0. Alpha plus I beta is one root of this. Now this cubic will have how many roots? 3 real roots. 1, q and r are real numbers. So if the coefficients are real numbers, then complex roots always occur in pairs. So if alpha plus I beta is declared to be a root of this cubic, then alpha minus I beta is deemed to be a root as well. So that means if this is a root, then alpha minus I beta will also be a root. But if even one of the coefficients of this polynomial was not real, then this would not have been guaranteed. And there is a third root, which is gamma. Now, do you also understand that the third root would have to be real? A cubic cannot have an odd number of complex roots, because complex roots are paired, right? So, cubic will always have at least one real root, provided the coefficients are real numbers, right? Now, sum of the roots is what? Sum of these roots is 2 alpha plus gamma. That will be the sum of the roots of this cubic, 2 alpha plus gamma. And what is that equal to? 0, because coefficient of the second highest power x square is 0. Yes or no? So that's going to be 0. So the third root turns out to be gamma equal to minus 2 alpha. The third root turns out to be gamma equal to minus 2 alpha. Yes or no? What we are seeking is a cubic whose one root is 2 alpha. That means we are seeking a cubic whose root is negative of the roots of this. Then you will have a cubic whose one root would be 2 alpha. So replace x by minus x. Then one of the roots will turn out to be 2 alpha. Yes or no? Right? So replacing x by minus x. So minus x whole cubed plus q into minus x plus r equal to 0. So minus x equal to minus 2 alpha will satisfy this, or x equal to 2 alpha will satisfy this equation. How's that? Fx is a polynomial with integer coefficients. What's given is fx, a polynomial with integer coefficients. With integer coefficients, right? Such that there are 4 distinct integers. There are 4 distinct integers, a1, a2, a3 and a4 are 4 distinct integers. These are 4 distinct integers. Such that f of a1 is f of a2 is f of a3 is f of a4 is 1991. The value of the function at a1, a2, a3 and a4 is all 1991, where a1, a2, a3, a4 are given to be distinct integers. Clear? We want to show that there doesn't exist an integer n. We want to be able to establish that there does not exist an integer n for which the function assumes a value 1993. We want to be able to establish that an n which is an integer does not exist for which fn is 1993. That means for no integral value of x which is n, the function could assume a value 1993. That is what we want to prove in this. Now, see, if I look at fx minus 1991, fx minus 1991, this will become 0 when x is a1, this will become 0 when x is a2, this will become 0 when x is a3, this will become 0 when x is a4. Yes or no? So this will become 0, this vanishes, this expression vanishes at x equal to a1, x equal to a2, a3 and a4, 4 distinct integers. Now, if this becomes 0 at x equal to a1, can I say that x minus a1 must be a factor of this? If a polynomial becomes 0 at x equal to alpha, then x minus alpha must be a factor of the polynomial. Could that be said? So x minus a1 must be a factor of this. X minus a2 must be a factor of this. X minus a3 must be a factor of this. X minus an must be a factor of this. So one thing for sure, if I seek to factorize fx minus 1991, then 4 factors are known to me. X minus a1, x minus a2, x minus a3 and x minus a4. The other factors, if any, could be kept in a black box, right? So if I need to factorize this, then this would be, say, x minus a1 into x minus a2 into x minus a3 into some gx, where gx would be some polynomial with integer coefficients, because fx is a polynomial with integer coefficients. So 1991 plus this will give me a polynomial with integer coefficients. So gx must be a polynomial whose coefficients are integers, to cause fx to be a polynomial with integer coefficients. Yes or no? Now, we want to show, and when you factorize something, are you creating an equation or are you creating an identity? You are creating an identity. If you factorize something, x square minus 1 is x plus 1 into x minus 1, that's not an equation, that's an identity. And it's true for all values of x unconditionally. X square minus 1 equal to x plus 1 into x minus 1 will be true for alpha, beta, gamma, delta, appa, kappa, jappa, sub, everything, right? So this would be true for all values of x. Right? Now, we want to show that fx cannot become 1993 for an integer n. Fx cannot become 1993 for a certain integer n. We want to establish that. What we do is, we deploy what is called the method of contradiction. Let us assume that fx indeed becomes 1993 for x equal to n, an integer. Let us assume that fx indeed becomes 1993 for x equal to n, where n is an integer. Let's assume the contrary. So put x equal to n on both sides, where n is an integer, right? So this gives me like a fn minus 1991 equals n minus a1 into n minus a2 into n minus a3 into g of n, putting x equal to n on both sides. No reservations writing this. Now let me assume that for this n, for this integer n, fn becomes 1993. So fn is 1993. So 1993 minus 1991 is 2. So I get 2 equal to n minus a1 into n minus a2 into n minus a3 into g of n. I'm sorry, and a4 also. Did I miss out on a4? I'm so sorry. There should have been an a4 all along, which I missed out and nobody objected to this. Why are you so goody-goody in the class? So there is a x minus a4 into gx, right? I'm sorry, fix this. X minus a4 into gx, right? So now if I plug in x equal to n on both sides, so I end up getting n minus a4 into g of n. Yes or no? What do you say? Putting x equal to n on both sides? Clear? Now, gx is a polynomial with integer coefficients. So g of n will be an integer. If the coefficients are all integers, then at x equal to an integer n, gx will be an integer? Yes or no? So this is an integer. a1, a2, a3, a4 are integers. and n is also an integer. So n minus a1, n minus a2, n minus a3 and n minus a4 are integers. This is an integer, this is an integer, this is an integer, this is an integer. Ah, shabash. And for sure, since a1, a2, a3, a4 are distinct, I have 4 different integers. These are 4 different integers. That means 2 for sure. Can you factorize 2 into 4 different integers? Can you factorize 2 into 4 different integers? Can you factorize 2 into 4 different integers? See, at best, minus 2, minus 1, 1. At best, 3 distinct integers is all that 2 could be factorized into. Yes or no? 2 cannot be factorized into more than 3 distinct integers. But apparently 4 distinct integers are already there, and there could be a 5th one as well. Obnoxious. This cannot happen. Right? Led to a contradiction. Factorizing 2 into 4 different integers at least seems obnoxious. It cannot happen, right? So this leads to a contradiction, and therefore we choose to conclude that the given assumption that fx indeed becomes equal to 1993 at x equal to n, an integer, is incorrect. No, I'm not debating that. You're right. For any prime p. So in that context, fx cannot become 1996 also, because then this will be 5, and you can't have the same. You're right, absolutely. Clear? Part 1. We want to show x plus y plus z to power m minus x power m minus y power m minus z power m when m is odd. M is odd. We want to show that this expression would be perfectly divisible by x plus y plus z whole cubed minus x cubed minus y cubed minus z cubed. We want to show that if m is odd, this will be perfectly divisible by this. This is what we want to establish. Clear? Now, one thing, x plus y plus z whole cubed is actually x cubed plus y cubed plus z cubed plus 3 times x plus y into y plus z into z plus x. I hope all of you know this result. X plus y plus z whole cubed is x cube plus y cube plus z cube plus 3 times x plus y into y plus z into z plus x. That means x plus y plus z whole cube minus x cube minus y cube minus z cube must be 3 times x plus y into y plus z into z plus x. 3 times x plus y into y plus z into z plus x. Right? This is an identity. This is an identity. This will be this plus 3 times this. Now, if I have to show that this is divisible by this, that means I have to show that this is divisible by this. If I can show that this is divisible by this, then the problem is solved. Right? That means if I can show that these are factors of this, that means if I can show that x plus y is a factor of this, if I can show that y plus z is a factor of this, if I can show that z plus x is a factor of this, then divisibility occurs. What do you say? If m is odd, for m equal to an odd number, I want to show that, say, x plus y is a factor of this. Similarly, y plus z is a factor of this. Similarly, z plus x is a factor of this. Which means x plus y plus z whole to power m minus x power m minus y power m minus z power m, when m is odd, let's say we venture into establishing that x plus y is a factor of this. Then x plus y will divide this, right? Now see, that means this would be something into say x plus y. If I factorize this, then this would be something into x plus y. What do you say? I plan to establish that this could be written as something into x plus y. Which means that if this could be factorized into something into x plus y, which means that if x plus y is 0, this must be 0 for x plus y. If m is odd, then this should become 0 when x plus y is 0, right? So let us examine that. So all that effectively you need to establish is that this becomes 0 when x plus y is 0 when m is odd, right? So let me take x plus y equal to 0. Let me take x plus y equal to 0 and see if this becomes 0 when x plus y is 0, right? Now if x plus y is 0, so this is 0, then we have like a z power m, right? Minus x power m. X power m would be what? Minus of y power m. X power m would be minus y whole to power m, minus y power m, minus z power m. Now m is odd, so m is odd. This anyways get cancelled. If m is odd, then minus y to power m would be minus of y whole to power m. So this will become like a y power m minus y power m because m is odd, which is indeed 0, right? Which means that x plus y indeed turns out to be a factor of this expression. Similarly, y plus z will be a factor of this. Similarly, z plus x will be a factor of this. That means this would be perfectly divisible by x plus y into y plus z into z plus x. How about it? Right? So if it is perfectly divisible by this, then this is perfectly divisible by this when m is odd. Got me? Oh my God. See, divisibility of polynomials. Please understand this. I'm glad you raised this because I'm sure there would be other people also who would have had this thought but were too scared to ask this. See, if there is a polynomial px which is x cubed and there is a polynomial qx which is 3x squared, say. When is px perfectly divisible by qx? So you should understand the concept of divisibility in polynomials, right? Qx is said to divide px perfectly if px by qx is a polynomial in x. In this case, what is px by qx? X by 3. Is it a polynomial in x? Yes. It just needs to be a polynomial in x. But what is qx by px? Is 3 by x. Is this a polynomial? No, it's not a polynomial in x, right? So in this case, px does not divide qx, but qx divides px because px by qx is a polynomial in x. That's when qx is said to perfectly divide px. This is what is meant by divisibility of polynomials. Please be sure about this, right? So this x by 3 does not interfere with divisibility. It's a polynomial in x, so divisibility is considered sanguine. Got me? All's good? Can I wipe this off? Okay, 15 part 2. 15 part 2. We want to find the condition necessary and sufficient for x cube plus y cube plus z cube plus k into xyz to be divisible by x plus y plus z. we want to find effectively the values of k, or the value of k for which this is going to be divisible by this, right? That means what? That means we want to find the condition so that x cube plus y cube plus z cube plus k times xyz could be written as some polynomial in xyz into x plus y plus z. That means this equal to this will be an identity, where this is another polynomial in xyz. That's when this is said to be divisible by x plus y plus z. Now, and this is an identity, which means this should become 0 when x plus y plus z is 0. That's necessary and sufficient. This should become 0 when x plus y plus z is 0. Yes or no? What? Right? So, I want to find the values of k for which this becomes 0 when x plus y plus z is 0. Right? So, now when x plus y plus z is 0, this should become 0. This should become 0. That means when x is minus of y plus z, this should become 0. Right? So in this expression, put x equal to minus of y plus z. Put x equal to minus of y plus z. So this expression then precipitates into, y plus z. Minus cube means minus 1 whole cube plus y cube plus z cube plus k minus y plus z into yz. This must be 0, replacing x by minus y plus z in this expression, and this should be 0. Now minus y cube minus z cube would get cancelled with y cube plus z cube. What you are left with is minus 3yz into y plus z minus k into yz into y plus z must be 0. This is what is required, right? Take yz into y plus z common. You end up getting k plus 3 equal to 0, right? Which gives you k equal to minus 3. K equal to minus 3. This gives you k equal to minus 3. So for k equal to minus 3, this will be divisible by x plus y plus z. In fact, I am not sure if you are aware of this identity. X cube plus y cube plus z cube minus 3xyz is x plus y plus z into x square plus y square plus z squared minus xy minus yz minus zx. You're aware of this? This is a routine identity. Clear? Shall we proceed? Can I wipe this off? Part 3. We want to find the values of n in the polynomial. Say this was a polynomial px, which is 1 plus x squared plus x power 4 plus x power 2 into n minus 1. This is a polynomial. And there is another polynomial qx, which is 1 plus x squared plus x power n minus 1. It's another polynomial. We want to find the values of x for which Px is divisible by Qx. Px is divisible by Qx. All right. Now, what is this? A GP series with common ratio and number of terms n. This is a GP series with common ratio x square and number of terms n. So this is x square whole to power n minus 1 by x squared minus 1. What is this? Again a GP series with common ratio x and number of terms n. So this is going to be x power n minus 1 by x minus 1. Right? Px by Qx must be a polynomial. Px should be perfectly divisible by Qx. Px must be perfectly divisible by Qx. What is Px by Qx? See, x power n plus 1 into x power n minus 1 divided by x minus 1. That's going to be x power n plus 1. And then x square minus 1 by x minus 1 would be x plus 1. That means the remainder of this division must be 0. The remainder of this division must be 0, yes or no? Right? Now, do you recall remainder when fx is divided by x minus a is given by f of a? Remainder theorem. Remainder when fx, this is my fx, and it's divided by x minus 1. The remainder of this division must be 0. How do you get the remainder of this division? Replace x by minus 1 in the numerator, you get the remainder of this division. Replace in this fx x by minus 1, you get the remainder of this division, right? So what's the remainder? The remainder of this division is putting x equal to minus 1 in the numerator. So minus 1 to power n plus 1. That's the remainder of this division. For perfect divisibility, what is required? This must be 0. Minus 1 to power n plus 1 will be 0 when n is odd. When n is odd. Right? So this will be perfectly divisible by this if and only if n is odd. Got me? Satyam Shivam. Satyam and Shivam. Ulta. My God, how do I manage to get this? Yes, for all you know. Demoralize कर देता है मेरे को. You know, I go wrong all the time. I get so demoralized. Come on. Can I wipe this off? See, polynomials can be in more than one variable. For example, you know, you would have a polynomial x cube y plus x squared y squared plus xy cubed plus 3, for example. This is a polynomial in xy. This is a polynomial in xy, right? So polynomials could be in more than one variable. Suppose there is a polynomial xy squared plus x squared y. Suppose this is a polynomial. Suppose this is a polynomial in xy. Say L of xy is this polynomial in xy. Now, what is L of y comma x? L of y comma x means replace x by y and y by x. So if you replace x by y and y by x, you get this. Now in this polynomial, for example, it's a special polynomial because in this L by x turns out to be the same as L xy. Turns out to be the same as L of xy. So if a polynomial is such that L of xy is the same as L of yx, then that polynomial is called a symmetric polynomial. That polynomial is called a symmetric polynomial. So this one, for example, is a symmetric polynomial. Got me? Now, now we have a symmetric polynomial p. Pxy is pyx. This is a symmetric polynomial. That's given. That's given. And x minus y is a factor of pxy. x minus y is a factor of pxy, which means if I factorize pxy, I could have written this as some x minus y into some polynomial q of xy. Yes or no? Right? Pxy could have been written as x minus y into q of x comma y. Clear? Okay, we want to find the remainder when p of xy is divided by x minus y whole square. I want to find the remainder when p of xy is divided by x minus y whole square. Clear? Do you all understand this connect here? Right? Huh? Okay. Now what is p of, if p of xy is this, what would be p of y comma x? P of y comma x means in this replace x by y and y by x. So this is like a y minus x q of y comma x. Right? Now p of xy is the same as p of yx because it's symmetric. It's given to be symmetric. That means this minus this will be 0. That means this minus this will be 0, right? So if I subtract, then I get 0 equal to x minus y into q of xy plus q of yx equal to 0. Oh, 0 already. Right? When I subtract, this is what I get. Which means q of xy must be the same as minus q of yx. Right? Must be the same as minus q of yx, right? This must be 0. Q of xy therefore must be the same as minus q of yx. Now put y equal to x in both. That means q of x comma x replacing y by x must be the same as minus q of x comma x. Can this be said? Can this be said? Which means what? Means 2q x comma x must be 0. 2q x comma x must be 0. Yes or no? Transposing? Which means q of x comma x must be 0. Yes or no? Now, we are done. So do you all understand everything that I have communicated so far? Huh? Now, having said this, realize that we just have to interpret this. We just have to interpret this. Q of x comma x means what? It means the value of q of x comma y at y equal to x. Q of x comma x means the value of q of x comma y at y equal to x. This is what it means. Q of x comma x means the value of q of xy at y equal to x. That is 0. That means in q of xy, if you plug in y equal to x, this will become 0. This becomes 0 in this expression polynomial q of xy. If you plug in y equal to x, this becomes 0. That means if this becomes 0 when you plug in y equal to x, that means q of xy must have x minus y as a factor, must have x comma y as a factor, so that when you plug in y equal to x, q of xy becomes 0. Yes or no? X minus y must be a factor of q of xy. Yes or no? Right? If q of xy becomes 0 when you plug in y equal to x, that means x minus y must appear in the factorization of q of xy. Right? See, if you plug in y equal to x, q of xy is becoming 0, isn't it? Right? That means x minus y is a factor of q of x comma y. X minus y is a factor of q of x comma y. That means p of xy could be written as x minus y into q of xy, which is x minus y into some other polynomial L of xy. Right? That means this is equal to x minus y whole squared into L of xy. That means x minus y whole squared must perfectly divide p of xy. That means the remainder must be 0. When you divide p of xy with x minus y whole squared, the remainder must be 0. Because x minus y whole squared perfectly divides p of xy. Yes or no? Got me?